Do you want to reduce the startup of your Java application from minutes to milliseconds? In this video, we will explore 4 approaches to making your Java services start up faster or even almost instantly. But first, let's look at the process of the Java application startup, because that's important for our further discussion. A Java service can start in several seconds, which is by itself already not that optimal. But what is worse, it can spend several minutes on the warm-up. Yeah, but what does it mean, the warm-up? Well, here's the whole process. First, the JVM and the application start. This is when the service is ready to accept requests. But it doesn't yet work to its full capacity. It means that it hasn't yet reached its peak performance, the performance that we all love Java for. So, naturally, next comes the warm-up stage. At this stage, the JIT compiler observes the running Java code and optimizes it for better performance. During the warm-up stage, the application accepts fewer requests than when it is at a stable state, and plus, it consumes more memory. What is worse, the process begins from ground zero every time you start the program. So, the existing approaches AppCDS, AOT Cache, GraalVM Native Image, and Coordinated Restore Checkpoint deal with various stages of this process. But the stronger the gains, the bigger the pain of integrating the solution. So, you should actually test all of them and choose the benefit-pain ratio that is acceptable for your situation. And now let's look at these approaches from the least demanding up. And we will start with application class data sharing, or AppCDS for short. The idea behind AppCDS is to load a set of system and application classes and store this data in a read-only archive. This archive is then used as a metadata by the JVM. And loading the classes from the archive is faster than loading them from scratch, so the startup is faster. With AppCDS, you can achieve about 40% better startup without the need for code refactoring. Using it is pretty simple. First, you need to start the jar file with the archive classes at exit option. When you stop the application, the archive will be created. And then you start this jar file again, but with the shared archive option that points to the created archive. Well, the benefits of AppCDS is that it works with most, if not all, hotspot JVM deployments. It doesn't require any code refactoring, and it doesn't require any complex process to be built up. And it can reduce the startup and even a little bit the memory use, especially if several JVM instances use the same archive. And well, basically, it's a good first optimization for Java 17 or 21 services. Well, the biggest disadvantage of this feature is that it does not remove the warm-up stage, and it does not reduce the warm-up, and we remember that this is actually the biggest problem. So it's a good fit for long-lived Java services where the startup is important, but not as important to introduce a more complex solution. Starting from Java 24, you can use AOT Cache instead of AppCDS. AOT Cache is a part of Project Leyden, which is being gradually introduced into the OpenJDK. AOT Cache builds on AppCDS but goes further. It records classes that were read, parsed, loaded, and linked during the training run. It also records method profiles, and in the future it is planned that it will also store precompiled code. So AOT Cache improves startup further than AppCDS. In the future, it should also improve the warm-up stage. To use AOT Cache with Java 24, run the jar file for the training run with a couple of options. Use AOT mode record and AOT configurations to record the application AOT configuration. But note that the services need a proper training flow, so run them through all representative execution paths. Then stop the application and create the archive with the option AOT mode record and AOT configuration pointing to the configuration file. Then start application with the AOT cache. With Java 25, you don't need to use this intermediate step of creating the cache. The cache will be created automatically when you stop the application after the training run. AOT Cache enables about 70% reduction in the startup time. Its benefits is that it keeps the normal hotspot JVM and JIT behavior. It doesn't require any code refactoring. It doesn't require any reflection configuration like with native image. And it's a promising solution for teams starting to use newer JDKs and that want to take advantage of Project Leyden, so they can start gradually and then work on that as the project gets introduced into the OpenJDK instead of jumping onto it somewhere in the future Java versions from scratch. But this feature requires JDK 24 or newer. Right now, it does not influence the warm-up stage, and the training run must resemble the production behavior, because otherwise the cache will not be that useful. So it's a good fit for services on Java 24 or newer, where you want to preserve the hotspot JVM and JIT behavior, and you want to reduce the startup, but don't want to deal with GraalVM Native Image. And speaking of GraalVM Native Image, that's the next solution we are going to look into. GraalVM Native Image enables ahead-of-time compilation instead of JIT compilation for Java applications. Ahead-of-time compilation, or static compilation, happens at build time, before the program execution. The GraalVM AOT compiler performs the static analysis of the code. During the static analysis, the compiler determines which program elements are used, and only these elements are going to make it into the final binary. Then the compiler compiles the application into a platform-specific executable. It starts in milliseconds and at peak performance because there's no standard JIT warm-up stage, because the code is already precompiled and optimized. Popular frameworks such as Spring and Quarkus support GraalVM Native Image out of the box. It means that you just need to enable the plugin to use it. And of course, you need the GraalVM distribution. You can use Oracle GraalVM, GraalVM Community Edition, you can use Liberica Native Image Kit recommended by Spring, or you can use Mandrill, tailor-made for Quarkus. So to use GraalVM Native Image with a Spring or Quarkus, in many cases is just a matter of one command. And then you get the native executable that starts in a second or even less, depending on its complexity. And there's going to be no warm-up. But as I already said in the beginning, the bigger the gains, the more complicated it is or might be to introduce the solution. So with GraalVM Native Image, there are some caveats or considerations. So for GraalVM Native Image, you need to provide the data on the usage of dynamic features in your application beforehand, or else the application executable may be built and even start, but then suddenly exit. In some cases, you don't need to do that. The compiler does a good job at detecting the dynamic features. And also with Spring in Quarkus, you also don't need to worry in some cases. But in some cases, you do need to provide some metadata about the dynamism in your application. So the benefits of GraalVM Native Image is that it provides almost instant start and no warm-up, right? So the application starts at peak performance. The memory consumption is often also lower, and you have a smaller attack surface, because only reachable code is included into the executable. But in turn, you get slower and resource-intensive builds. So the native image requires several gigabytes of memory to be built, and also the process may take several minutes. You get the platform and architecture-specific binaries, so the run-everywhere principle does not work in this case. The dynamic features may require extra configuration, and also well, the profiling and debugging process is going to be a little bit different because it's not your familiar JVM, right? It's a native executable and it's a different kind of code. I would say that it's the best fit for serverless, for scale to zero approaches, for CLIs and services where cold start latency is more expensive than build complexity. And then, last but not least, coordinated restore at checkpoint, or CRaC for short. CRaC enables you to create a snapshot of a running and warmed up Java service, save it to the file, replicate this file among cloud instances, if you do cloud deployments, and then restore the application from this file from the moment it was paused, like a video game. This way, the application will always start in several milliseconds, regardless of its complexity, and always at a warmed up stage. But at the same time, the hotspot JVM is still there, the JIT compiler is still there, so dynamic performance optimization is still possible. If you want to try out the CRaC project, you need a dedicated JDK build with the CRaC support. Some vendors, including Azul and Bellsoft, provide JDK builds supporting CRaC. Also note that CRaC works only on Linux because under the hood it uses the Linux technology called CREO. So in the simplest possible scenario, you just start the application with the right JDK, and then with JCMD you make a checkpoint, and then you restore the application from the file. Well, that sounds a little bit too good to be true, right? Well, yes, there are some considerations when using CRaC. I have just shown the simplest scenario, but it is almost never the case. Java applications are not as simple as that. And so connections, sockets, files, thread pools, credentials, and other external resources cannot simply wake up and assume that the world stayed the same while the process was frozen. And so in many cases, you will need to add additional methods before checkpoint and after restore to close all the resources safely and then restore them also safely and reliably. So it means that you will need to do some code refactoring. Also, some technologies do not support CRaC out of the box, so you will have to write your own logic on befriending them with the coordinate restore checkpoint. Another important thing to note is that the technology preserves the exact state of the application. It means that the snapshot may contain sensitive data. So you need to consider that as well. So the benefits is that you get very fast, almost instant restore with a warmed up JVM. The JVM and the JIT compiler is still there, so it's your familiar Java code and Java processes. And while it's a strong option for services with expensive initialization and predictable warm-up. But in turn, you require a JDK with the CRaC support and compatible operational environment. You may need to do some code refactoring. But in turn, you need the JDK with the CRaC support and a compatible operational environment. External resources may need deliberate lifecycle handling, and you may need to do some code refactoring. I would say it's a good fit for Java services with expensive startup and warm-up, stable deployment environments, and the team willing to manage the snapshot creation and restore safety. To sum up, I encourage you to try out all of these solutions and see which one fits your project best. In the description, you will find links to dedicated guides on using each of these technologies, so you can study them in more detail and experiment with them. If this video was useful to you, don't forget to like it, subscribe to our channel, and until next time!